I'm James Atlas. I'm a senior lecturer in computer science at University of Canterbury, but also part of the Mars team in general. And the work that I'm kind of talking today about, I've aimed hopefully at the audience here, which is partly getting up to speed with AI in spectral photon counting CT image reconstruction, and showing you a bit of what we're currently working on with the student Theo Dapamide, who's a University of Otago student and part of the Mars team as well, and then looking a bit at future work that we're trying to take on. So as a brief kind of overview of talk, which is only 15 minutes, so target for questions here. Beginning, I'm just going to introduce the idea of a spectral photon counting CT image reconstruction pipeline and the concepts behind artificial intelligence, really from base principles on to the point where we can say, where is this applicable within this pipeline? All right, and then we're going to look at some approaches. Some of them are current approaches in that this is the active area of the state-of-the-art out there with regular computed tomography, and in what we're doing to try to bring some of those concepts into spectral computed tomography. All right, and then we'll kind of show some future directions there. So the basics here, if you're familiar with the Mars project, they have a special technology that can detect different photons at different energy thresholds simultaneously, which means they can record on a detector a signal coming through some particular, you get a sort of a body of a person there at multiple energy thresholds. What this means is that we actually get spectral information about the attenuation properties of the X-ray that passes through the specimen. All right, that means at the very beginning of a data processing pipeline, you have some kind of photon counts at each of these energy levels, energy thresholds. These can be considered to be spectral projection images, or sort of what happened during the scan. Now, there's a lot of geometry and a lot of sort of pre-processing and what I would say computer or electrical engineering components of this, mechanical engineering. I'm not involved in those directly. Maybe at some point we get to that point. But what I'm talking about today is taking that data set from projection space all the way to, through an imaging chain, to a three-dimensional reconstruction of materials. All right, so that's the general goal. It currently is satisfied with an imaging chain already. It works very well in preclinical settings. So what we're trying to do is to improve either one of two objectives with AI, the actual quality of the final images, right, or the speed. Right? And those are actually closely related to each other because many of the techniques used in their model-based iteration, the more processing you're able to give it, the better result it's able to find, right? So the general idea is in AI, we can either improve quality or performance. Both of them lead essentially to the same thing, right? So we're going to improve quality. How do we do that? Right? One of the ways that we do this is sort of this concept that machines could have some kind of intelligence that either mimics what we do or in fact reaches beyond what we do. And so I'm going to give you a brief background on artificial intelligence because it's often used as a buzzword for describing magical things that computer scientists and data scientists and other people do. All right? What I want you to say is it's not magic after today. I can see what it's trying to do, and we're going to try to define that up front. So what we're not doing here today is broad artificial intelligence. All right, broad artificial intelligence usually means you've got some kind of actor or agent that is interacting with an environment. It has to have automation. It has to be able to take actions and do things like that. We're not building the next Skynet or something like that. What we're trying to do is to do less about the automation or giving an agent control to take actions in an environment, and much more about sampling that environment in such a way that we understand the properties, or as is often said, the patterns that are there, and to train it to learn the patterns that we would like to find. All right. In particular, most of the buzz that surrounds AI right now reduces down to a subset of AI called machine learning. Right? Machine learning has many subtasks that it can be applied to. If you've ever looked up machine learning or AI or read an article about it, one of the first tasks that you look at is image classification, which says, great, we can essentially do computer vision using a machine to do things that we might do as a human, which is to say there's a cat in this picture. Or more specifically, where is that cat in this picture? Or even more in depth, how many cats are in this picture? Or if I took an entire scene, can you segment it into the instances of cats, dogs, trees, all of that? All right, so that's kind of where the buzz is surrounding AI right now, is within this machine learning setting. All right, I want to define machine learning for you in a way that makes sense, and hopefully you can take this away today. So machine learning is equivalent to the idea of function approximation. All right, most of us have written some kind of computer code at some point, which we take in input, we have some function, or a very complicated function, an entire program that's a set of thousands or even millions of functions, but it's still just a function that takes that input and produces some output. All right, so we've done that, great. We can model that mathematically as just taking in x, applying some function f, and outputting y. All right. The general idea of image classification is simply this. We're taking in an input of a picture, and our output should be a label for cat. All right, what goes in between is some kind of algorithm for image classification. All right, we can write these by hand, and people used to do this a decade or more ago by trying to figure out what kind of pattern represents a cat. Let's program it to detect that pattern in a picture. All right, but we found out very quickly that that is only so good. In particular, cats are not well defined. All right, and so the question of how we go from an input image to an output label is sort of a goal that we would like to learn rather than hand program in our own features. All right, so what we're going to say is that machine learning gives us the ability to do this, which is to create an approximate function in here that can perform the task. All right, we're going to go quickly through this, but our goal is to do this, which is essentially say we're not writing the program. We're actually going to try to approximate the program based on what we expect it to output. All right, so in general, these deep learning advancements have done things like help navigate self-driving cars by doing instance segmentation, like I mentioned, finding all the things in one scene very quickly. And they can do language translation at an incredibly high level right now. They can do all sorts of interesting style transformations between input space and output space. They can even do reinforcement learning to learn to play video games that many of you might play. They kind of can do this. How we get there is to understand what's in that middle section where I said we're learning an approximate function. All right, it's not as easy as just saying, great, let the computer do it for me. All right, what we're going to unwrap is what goes into that approximate function here, and then we're going to apply that to the domain of spectral photon-counting image reconstruction. All right, so what goes into that little box in the middle is a whole bunch of smaller components. Now, if you remember in your programming days, you probably have some operators like multiplication, addition, conditional statements, things like that. All right, what we've done is just define this mathematically as a set of operators that are placed into a neural network. All right, convolution is a mathematical operator that just takes a matrix in, multiplies it by a kernel, and outputs the resultant matrix. All right, so it's matrix multiplication. That's the program here. All right, that is the first element of a neural network. It allows you to take some kind of input, which would be a picture, apply a convolution to it, which changes that image or transforms it into another layer. All right. Common convolutions, so you could have averaging filters, median filters, XOR filters, all sorts of small level components. All right, so the goal here is that we've set up a matrix multiplication operation on our input and generated some output for it. Great, that looks good. In a general sense, that only gives us one piece of the puzzle. The other big piece of the puzzle is we need some kind of conditional logic. All right, we're putting building blocks together. I'll show you how they work in just a second. We're going to run these through an activation function and a pooling function. What this gives us is the ability to do nonlinear function representation. So if we need conditional logic, all we need to do is to simply run it through a piecewise function. A ReLU is a piecewise function. We'll go into the details in a mathematical course, but the idea here is we have some basic building blocks of a computational flow. We're going to take the input, going to run it through some matrix multiplication, run it through a activation function, which is going to filter that based on some conditions. Then we're going to do that again at another layer, and again at another layer, and again at another layer. Eventually, we filter all of these things down to some set of features. And you can see that here in the green layer that's over here. And then we eventually make a decision about those items that we've filtered all the way through and generate some output. All right, these are your basic building blocks, and the idea behind it is in machine learning, we actually just create the structure for it, don't put anything in there other than initial random values, and we just say, give it your best guess. It's like writing a program by literally blindly typing in code, running it, and saying it doesn't work. How do I fix it? All right, this is what a machine learning, deep learning pipeline is. We set it up to have enough matrix multiplications so that it can get the features that we're trying to learn, but its initial guess is going to be terrible. It's not going to guess a cat, it's going to guess randomly. All right, and so then we have to train it. We have to give it enough data to say, you were wrong about your prediction or you're wrong about your output. All right, and we're not going to get into the math of gradient descent algorithms, but because we structured our network in the way that it is up here, we can actually tell not only were we incorrect that it was a cat, where in our network were we incorrect. And so we can use a backpropagation algorithm to compute the loss or the difference between what we were expecting and what we produced, and go back and fix this network to get it closer to the function we're trying to approximate. All right, that's a short background on deep learning in a general nutshell. To take this a step further, we take those building blocks and we put them into architectures that can solve different kinds of problems. All right, so cat classification is not particularly useful for spectral photon counting CT. So there are other networks that can take the input, compress it to a latent space representation, and then uncompress it to another reconstructed output. What this enables us to do is to learn the underlying representation of something, all right, and then use that representation to sort of regenerate what we would have expected. And so if you've done iterative reconstruction before, this is essentially your forward-backward pass of saying, what is the underlying model? Let's take a guess at it from our input, all right, and let's take that model and essentially reconstruct what we would have expected to see, and then we will take this and tune the network so that it's very good at modeling this over multiple pieces of data. All right, so these are our fundamental structures. There are all sorts of other techniques added to the networks to give it additional depth or being able to learn for multiple situations. These deep learning network architectures are sort of evolving as we speak. The most current ones use densely connected networks that pass a lot of information through from the beginning to the end. All right, so I'm going to give you two learning paradigms and two kind of places where these exist within the image processing pipeline. One is a supervised learning, where we say, great, we've created this giant network that's got all of these operations in it. We have expected output. We can tell it, here's what we're expecting you to output. All right, go ahead and fix the network to match it. We also have something called self-supervised learning, where we don't have a known output, and this is often the case, where we have some kind of input, and we generally have a guiding function or a loss function that tells us what's the quality of the output. We don't necessarily know what the output should be, since nobody has done that ahead of time, but we know some metric that allows us to guide it to find a better output. All right, that's self-supervised learning. All right, so where does this actually happen within a pipeline as complicated as spectral reconstruction? All right, so I give you the idea that we're taking this as a not quite a black box, but a procedure that goes from spectral projection images to a 3D reconstruction. All right, in between, we can insert this artificial intelligence or deep learning network at multiple places. We could substitute it for the entire pipeline. We could take a spectral projection image, train it to produce a three-dimensional material output. All right, currently this is not quite possible. I'll show you some initial things at the end. It's very computationally expensive to do that, and it requires encoding the entire reconstruction algorithm essentially as a neural network. All right, but what is more common right now is to apply deep learning either before or after some either filtered back projection or iterative reconstruction algorithm. All right, so I'm going to kind of give you an idea of how we're doing that and how it can be done and why it's useful. All right, so applying it either before or after essentially turns it into a artifact removal and denoising algorithm. All right, so it's saying we know that there are some parts of the signal that are noise, and we would like to filter out the noise and keep the signal. All right, how do we actually do that in a neural network? All right, one simple approach to this is to use that encoder-decoder network that I structured earlier, where we take input, we compress it to a latent representation, and then we reconstruct something from it. All right, so you can see here a small pipeline with that encoder and decoder. And what we've done is we take an original image that doesn't have any noise in it. We apply some noise function to it. Then we feed that noisy image into the network and say what you should predict is the clean output. All right, so this is a semi-supervised algorithm where we give it just the noise pattern. All right, so we don't necessarily know anything about what it should produce other than we had an initial clean image. We give it a noise pattern and say it should produce whatever it is without the noise. All right, so this is something that we are currently working on. I'll show you what this pipeline looks like. It is using an FC DenseNet, which is a UNet style architecture. You feel free to ask me questions about this later, but it is taking that DenseNet blocks that were shown earlier and applying them to the input, all right, to generate an output. Sorry, I can't point here. Taking the input, passing it through multiple layers to extract features that are relevant to the latent representation of the object, and then reconstructing it without, hopefully, without the noise, and then comparing that result to the original input. All right, what we're actually doing right now, work with Theo, we're trying to model noise functions and various things that could impact the image in reconstruction space, so post-IR. This image could be sent through a simulated phantom with simulated added noise to it, all right, and then we would ask it to essentially remove that noise. That's allowing it to detect spatial resolution features or sort of noise that's based on locality. It's also able to detect noise on general properties such as the scanner or other setup. And so it can remove patterns that we introduce to it from the data sets that we train it on. Once we've trained it on these particular noise patterns, if we gave it an image that didn't have sort of our simulated phantom, we actually apply it to a regular data set here, it will remove more noise than other filters and processes. This is the current sort of state-of-the-art in regular computed tomography reconstruction. So this is within the last 2 to 3 years, deep learning reconstruction has been applied to sort of single energy computed tomography, and this is how they do it. They essentially introduce a noise function or some sort of semi-supervised learning by scanning something either with a low dose of energy and a high dose of energy, or high dose of radiation here, and then training the network to go from a low dose image to a high dose image, all right, with the same kind of network structure that I just showed you on the previous, where we're training it to learn that mapping. All right, we can also do this with the computational cost, and so we could have a very complex iterative reconstruction algorithm that gives us essentially as good as we can get. All right? And if we train an algorithm to take it from a low-cost computation to then apply a transformation to it to make it look like or sort of reconstruct at a higher cost computation, that's a different way of doing it, but it also is the same structure. Essentially, we're taking in some kind of image, some noise, and denoising it by producing the output that's at a higher quality. All right, so we are generally working at this stage right now within the Mars project to do image denoising and turning sort of lower quality reconstruction or sort of speeding it up by trying to predict what a higher quality reconstruction would look like. There are efforts out there that are trying to map the actual reconstruction algorithm into a neural network. Some initial results on a mapping between the classical filtered back projection algorithm and a neural network are available. We have a student looking a little bit at mapping this with the SART algorithm and stuff that's used within the Mars project. This is a very complicated series of work because you need to translate all code into a neural network, and they tend to need approximations even in that because you're talking about terabytes of parameters and unable to load that into memory. So this is currently what's sort of active research in the community to try to map the underlying algorithms into a deep learning network. What that would gain us is the ability to not have to model all of the physics of the problem. And I'm not a physicist, but some of the physics that has to be placed into a model-based iterative algorithm is very complex. Right? In this case here, if we actually know a guiding function of what it should look like at the end, we can actually allow the network to learn that. So it does learn the physics, but we would need enough essentially either synthetic data or real data to get there. But some initial results are promising that we can at least take the original filtered back projection algorithm and map it into a deep learning network. All right, other future directions for the kind of employment of these techniques. This doesn't have to do specifically with an image reconstruction pipeline, but more so with the identification of materials that are in a particular scan without knowing ahead of time what those materials are. Right, so there's a concept of self-supervised learning, or sort of on the left you see an initial clustering of materials that were in a particular scan, and on the right you can see the sort of results of taking an autoencoder to learn what patterns represent a certain kind of material. So if we learn the pattern that represents HA, or the pattern that represents water or lipid or some other kind of material, we can then apply that to a particular scan and perform a clustering based off of all of those, which means that if, say, there's a new material, it would show up as essentially outside of the cluster space, or sort of more distant from any material that we've already known. We can also use this to do calibration during a scan. So if we were to take that same model from a sort of early scan and then apply it during a scan, we can actually look at the difference between these clusterings, or the difference between the latent representations, and it might help us to know which materials are which, and to sort of recalibrate based off of current data, right? Not just a phantom that was scanned last week or 2 weeks ago. All right, so these are some things that we're kind of working on currently. Yeah, I'll end here for questions.